Welcome to Astronomy 103. In this module, we will talk about the night sky and phases of the moon. In order to start understanding how do we look at the night sky, it's first best to think about is how do we figure out where we are on planet Earth. So, if you didn't know the names of countries or where places are, had no GPS or anything else, and you want to describe a location on Earth, the only way to do so is to use latitude and longitude. Latitude lines go from the equator, which is at 0 degrees, all up to the pole, which is 90 degrees, and down the south pole, which is basically 90 degrees south or so. And longitude go basically around essentially 100 and 360 degrees roughly. All right. Okay, so that's basically how you can find yourself on planet Earth. Okay. Now let's basically try to figure out how we can do this for the night sky. All right, so if you look up at the night sky, for instance, if you look at this lower panel right here, this is the Orion, the Hunter. Okay, it's a constellation. So constellations are parent groups of stars, right? But the stars in constellations are usually far from each other. So for instance, like you can see here in this little plot, that some of the stars are very, very far from each other. They just look close together in the sky. So they're just close. They appear to be close together in the sky, but they're actually in fact really, really far away, all right, from each other. All right, so they appear to be roughly in the same direction as seen from Earth. Now, because these patterns are rather distinct, constants were picked out by the ancient Greeks and given Greek names. All right, and so because many of these constellations are up in the sky, roughly speaking, the sky can be divided into the areas where constellations are. So the sky is roughly divided into some 88 pieces, each given a name of ancient constellation that it contains, so that every star, every point in the sky officially belongs to some constellation. Okay. So picture below shows the very distance to the stars in Orion, the brightest constellation in the winter sky. So you see this winter, you see that these stars are actually quite far away from each other. Okay, so if you can imagine night sky as basically this like sphere around you, because actually you can't tell how far away the stars are. You can imagine you have a ball around you, and at the edge of this ball, someone has pricked the surface of the ball to basically allow light in from the outside. So you see these like points of light. That's basically what this night sky sort of appears to be, right? So the sky has the appearance of a sphere, right? And because the Earth rotates, at night, the entire sphere looks like it rotates, right? So the name given to this big imaginary sphere is called the celestial sphere, right? And the celestial sphere appears to rotate basically once a day from east to west, right? It actually, in fact, rotates around the north celestial pole. So if you look, the stars, as we'll discuss later in this module, appear to rotate about two central points: the north celestial pole and the south celestial pole. We will deal with the north celestial pole mainly because we live in the northern hemisphere. Okay. All right. Now, um, if we uh, look at the northern hemisphere, uh, you can describe basically where we are. So, for instance, if you look up at the night sky, or even day sky, if you look directly above you, that's zenith, right? And if you look off to the side, basically, you see basically the horizon around you. Okay, so there's be a horizon and a zenith, and what happens is that basically it takes about 24 hours for the entire sphere to rotate, because it takes 24 hours for the Earth to rotate on its axis, right? So every hour or so, basically, it's 360 divided by 24, about 15 degrees. So stars move about 15 degrees every hour east to west, roughly speaking. All right. Now, let's talk a little about the North celestial sphere. So why does it look like a sphere? Well, it turns out, like if you take a sphere and you spin it, right, there's always going to be a point which doesn't spin, right? Um, or doesn't move in essence, right? And so this here is the north celestial sphere, and there's a counterpoint on the southern hemisphere called the southern celestial point. And around these points, basically, stars appear to rotate around these stars, right? Now, it happens to be the case in the northern hemisphere. There's a star called Polaris, which is also called a North Star, which is very close to the northern celestial point All right, and so stars appear to rotate in circles around Polaris as a result of that. All right, so in fact, basically, the sun also rotates around Polaris. It's just basically off of 90 degrees, so it might rotate something like this, go above the sky, and then come back down again. All right. Now, if you're close to Polaris, or you actually are Polaris, right? You never rise, you never set, right? You don't see it in the daytime because this is the sun's blots it out. But basically, if you could see during daytime, you would see basically Polaris as well. So stars that never rise, never set, just appear to spin around Polaris, right, are called circumpolar stars, all right? And so what is interesting, basically, is that this star is so unique is that if you can find it, you can always tell basically where north is. And also, more interestingly enough, if you basically move toward North Pole, what will happen is that Polaris will be directly above you. If you move to the equator, Polaris will basically appear at the horizon. And so basically the position of Polaris tells you basically how how high up in latitude you are, or another way to think about how close you are to the North Pole. Right. Okay. Um, so this is the same thing as, again, basically if you see it, if you're at the equator, Polaris is at the horizon, so you don't actually see it. If you try 1 degree north from the equator, Polaris will be 1 degree above the horizon. So by the time you reach North Pole, Polaris will be directly overhead or at zenith, right? And so what's interesting about this is that the altitude of Polaris tells you basically your latitude. So for instance, if Milwaukee is 40 degrees north equator, if you look at Polaris, Polaris will be 43 degrees above the horizon, right? Okay. All right, so now we have some idea of basically what the celestial sphere looks like. You can divide up the celestial in a similar way that you divide up the Earth sphere into latitude and longitude, right? So the difference is basically there's going to be something called declination, which is degrees north or south of the celestial equator, right? So basically relative to the equator over which the celestial sphere rotates, which is also the same as the Earth's equator. And right ascension, right? So basically measure hours, minutes, seconds eastward from the position of the sun at vernal equinox, right? We'll figure out what that means soon enough. Okay, so let's talk a little about basically Earth's motion and the day-to-day changes to see in the star. Okay, so stars are really, really far away compared to the sun. Sun is basically 1 AU away or so, maybe about 10 to 13 centimeters away, right? But stars are much, much further away than that. Okay, and so what's interesting about this is that if you have a star, let's say the star is over here, okay, and you take some time to spin, all right, over that time. What happens is that during that day, the Earth also revolves around the sun, right? So there's actually 2 days you need to worry about. There's one day, which basically takes a star to rise, set, and basically come back to the same position as it was before. This is what's called a sidereal day. And there's another day, which is the time it takes the sun to basically rise and set and come back basically to the same position. All right, now the difference between these two is a very tiny angle. All right, what's that? How big is that tiny angle? Well, it turns out that basically it's about 1 degree because it takes 365 days to go around the sun, right, for the Earth. So that's 360 degrees and 365 days. So 360 degrees divided by 3, that's basically 0.986 degrees, with about 1 degree or so every day, right? And so the Earth has to rotate extra degree every quote unquote day in order to maintain a solar day. And that's what we used to think about as a day, is a solar day, right? But a sidereal day is basically slightly shorter by a small amount. Okay, so how much smaller is it? Well, the difference is it has to rotate an extra 1 degree, all right? And it takes basically, so 1 degree is about 1/360th circle. So it takes 1/360 of 24 hours, which turns out to be an extra 4 minutes, right? So what that means is that basically relative to a sidereal day, a solar day is 4 minutes longer, right? So what that means is that because we measure everything in a solar day, that stars, let's say a star rises at a certain time at a particular day, the next day it will rise 4 minutes earlier because its quote unquote day is shorter. All right. Okay. So for instance, like we take the example of Betelgeuse, right, brightest star in Orion. Betelgeuse arises at 4 p.m. Say, okay. Tomorrow will rise 4 minutes earlier at 3:56, and a month basically will rise basically 60 to 30 times 4, 120 or 2 hours earlier. Okay. Okay, and after 24 months, it'll rise basically 24 hours earlier, which would be the same time, right? So after about a year or so, it'll rise at the same time. All right. So this is really an interesting thing, right? Because you could basically, base on the rise time of a star, you could essentially use it as basically a calendar at some level. Okay. Let's see. So let's talk a little about basically Earth's motion, right? So in a year, the Earth basically rotates around the sun, so that's 360 degrees, right? And so every day moves basically about 360 divided by 365, 360 degrees divided by 365 days, about 1 degree or so, right? So basically, if you looked at the sun relative to some background stars, the sun will appear to move about 1 degree um, uh, east to west, basically, every day, right? Okay, whoops. And so what happens is that the sun will move over the constellations that it's basically behind. So for instance, if I look at March, all right, um, uh, if I look at March, for instance, and I can look basically through the sun, I can see basically it's in Pisces and stuff. In December, I can see basically it's Sagittarius, for instance, right? And in June, say, I can say basically it's Gemini or some other winter months or so, okay? So basically the sun will move through these uh, um, uh, uh, constellations over a course of a year, right? And so the path the sun sweeps out against these background constellation, background stars, is called the ecliptic, right? Now let's talk a little about seasons, right? Seasons are the result of the tilt of the Earth. So it turns out that the Earth's rotation axis is not perpendicular to the plane of the Earth's orbit around the sun, right? So it's tilted by 23.5 degrees, right? So basically the plane of the equator, which is the celestial equator, or also the Earth's equator, is 23 degrees relative to the orbit of the Earth, right? Okay. Now this has very important effects for seasons here, right? So during summer, say summer solstice, June 21st, the longest day of the year, the sun is basically highest in the sky in the northern hemisphere. Winter solstice, basically is December 21st, with the shortest day of the year, the sun is the lowest in the sky in the northern hemisphere. And basically vernal equinox and luminal equinox, the sun is directly above the equator. So there are 2 times a year the sun will be directly over the equator. Okay, and so what that means is that basically relative to the celestial equator, because the orbit, the tilt of the Earth is 20 degrees relative to the orbit of it around the sun, which is defined by the ecliptic. If we look at basically the celestial sphere, the ecliptic is going to be inclined at 23 degrees relative to the celestial equator. Right? Okay, so as a result, right, you can think of it 2 ways, right? So you could look at this plot as the easiest. This plot is more what you might see. Okay, if you look at during summer, the sun is higher in the sky, right? And as a result, the sun is more direct on the surface of the Earth, so basically you get more sun, and then it's up longer than it is than it is in the winter, so you get basically more warmth. In the wintertime, on the other hand, the sun is lowest in the sky, and so the sun's rays are less direct, and also the sun basically stays up a lot shorter than it did in the summertime, right? So that's basically one way of looking at it. The other way of looking at it is basically looking at relative celestial equator where the sun is going to sit. So on March 21st or September 21st, when it's above the equator, that means the sun and the celestial equator are the same path now. It'll follow this path across the sky. It'll follow along the celestial equator. However, basically in the summer months, it's going to basically fall above the celestial, so it'll be higher in the sky. It's going to be longer up in the sky as well, right? As opposed to winter, basically, where it's lower in the sky, and so you get less direct sunlight, and as a result, basically, you get colder climates. Right. Now, that's not the only motion that the Earth suffers from. There's also additional motion as well, and this motion is called precession. Right. So, you ever play with a top, and you set the top spinning, and you don't point it directly down? What will happen is the top will slowly tilt basically as it spins. So it spins really fast here, but slowly tilt. The axis of the top will slowly rotate around a larger circle. Right. Now it turns out the Earth does the same thing. Right. What's required for precession is just a little bit of imbalance here. So the support is here, but the center of gravity of the top is here. So basically there's an imbalance, and the force here is basically off center from here. Okay, so any sort of off-center forcing will cause a precession in a rotating body. And so how do you get off-center forcing? Well, it turns out you get off-center forcing from basically the sun and the moon exerting a force on the Earth's bulge or tides, all right? And so as a result of this force, basically the Earth's axis also slowly precesses over a period of many, many years. How long is this precession? Well, it turns out it precesses over a time scale of 26,000 years, right? And so basically, if you look up at the sky, the Earth's axis, which is what the north celestial pole would be, will basically move over a period of years. So for instance, basically, we're right now here, okay? And because we're here, the North Star is Polaris, right? However, if we wait 13,000 years, so then in this case, the North Star is no longer Polaris, but rather Vega, right? And so basically, you also look backwards in time. At some point, it was Thuban as well, right? Now, what's amazing about this, right, is that this effect was first discovered by the Greek astronomer Hipparchus, right, in about 150 BC. So it's around right about here or so, okay? And what he did was he saw the position of the sky on the same day of year, had changed slightly over 50 years, had made observations. So basically, he looked at the night sky every year for 50 years, and he knows the positions of the stars, stars in the sky move ever so slightly. All right. Whoops, hold on. So let's see. Okay, so this is an amazing act of basically observation. No telescopes, no nothing. Just measuring the positions of stars using very crude instruments. Right? You do over long enough, you can see that in fact the Earth actually slowly precesses. Okay, so here is the relevant thing, all right, which is very important. One thing that is clear, if you look out at the night sky over the course of a month, is that the moon has phases, right? So let's talk a little about phases of the moon, right? Now, let's see. So the moon is not a star, right? The moon is a big rocky body, and so it doesn't generate its own light. It must shine by reflected sunlight. Right, and so basically the only parts of the moon we see from Earth is the parts of the moon that are lit up by the sun. Right, so let's look at this picture here to try to understand basically how the phases of the moon come from. Right, so in this picture, basically you see the Earth is rotating. You're sitting at the equator. The moon is also orbiting around the equator, and the sun is really, really far away relative to everything else, right? So it looks like a parallel beam moving in from a great, great distance. Okay. Now, over the course of a month, the moon will basically go around its orbit, so go around and come back again. And over the course of the day, basically you spin around the Earth, basically go from basically sunrise to noon to sunset and to midnight. Okay, so let's look at this picture very carefully. Right, so there's the Earth. It's going to spin around 24 hours. There's the moon. It's going to go around in basically over the course of a month or so. Right, and so at any point particular night or day of a month, the moon will be at one of these positions. It'll be here, or 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 somewhere in between. Okay. Right. But you, on the other hand, over the course of a day, will basically change positions, right? You'll basically go from through sunrise, through noon, to sunset, to midnight, and back to sunrise again, right? Okay, so we're gonna basically look at this thing and understand basically the phase of the moon, all right? How do we get the phase of the moon? And then secondly, the relationship between phase of the moon and the time it rises and sets. All right. So let's see. Right. So we're gonna do this a little bit easier. I think the best. Let me think about how the best way to do it. All right. So let's do it this way. Okay. All right. Okay. So I think the easiest way. I'll talk through this example, and then we'll do some exercises. All right, because that's probably easiest. All right. So um. So let's see. So you're gonna go through sunrise, noon, sunset, and midnight. All right. Okay. And now let's look at the position of the moon at every point in its orbit. So new moon, there's nothing facing the Earth, right? So only you see the unlit side of the moon. I'm not gonna say dark, all right, because dark has a different notation for the moon. I'm gonna say the unlit side of the moon, all right. So you look up, there's nothing there, okay. You look up basically at waxing crescent. This is what you see here. If you look at the sky at this point, you only see a tiny sliver because only this part of the moon, if you basically draw a line here, right? Only this part of the moon is actually visible, so you see basically waxing crescent. If you look up basically a little later, right, when the moon is at first quarter, so half the moon is lit, but we can't see the other half of the moon that's lit. We only see basically the half that basically faces toward us, and so the half that faces toward us, basically one side is lit, one side is unlit, and that's called the first quarter moon. All right. Okay. And now basically, if you go a little further, right, then at this point, basically more of the side of the moon is lit relative to you, and so this is called the waxing gibbous, right? But not complete amount. Then basically you have full moon, then waning gibbous, then the third quarter, waning crescent, and then back to new moon again. All right. Okay, so this is basically talking the same thing. I'll let you guys read it. All right. All right. And so we're gonna talk a little about this, and then we're gonna talk a little about how the sun rises and sunsets. All right. I think the best way of doing this is to do an example. All right. Let's see here. All right. Well, okay. Maybe I'll come back to this point in a second. All right. So it's best to try to do an example here. All right. So what I'm going to do is stop this, and let's go to an example here. All right. So the first thing to understand basically how the phases of the moon work, all right, is to always be able to draw a picture or rely on a picture or interpret a picture. Okay, so let's do that real quick. Okay, so the first thing is that let's draw the Earth here. Okay, and let's draw the moon. Let's draw the sun. So there's the sun. It's so far away that it's just going to be lit up as parallel light rays. All right. Now let's draw the moon. I'm going to basically draw the moon. I'm going to draw a few things. So the way I like to draw it is I like to draw it in terms of basically the full moon first. So let's draw the full moon because that's the easiest. All right. So this is the full moon. I'm going to do the dark side as hashes right here. Okay, so that's full. And then let's draw new here. So where's the new moon? The new moon is, I have to be careful to make sure this thing's locked. Okay, so that's locked. Hopefully it's locked. And there's the new moon. So that part is lit. Whoops. This part's dark. So this is new. Okay. And now I'd like to do the first quarter. The third quarter. The way to think about the first quarter and third quarter is it's not quarter moons, it's actually the phase, right? So for instance, like the phase of football games, this is the first quarter, second quarter, third quarter, fourth quarter, right? Okay, so this is the third quarter. Okay, and now we can do the crescents and the gibbuses. So this is crescent, gibbous. Okay, more gibbous, more crescent. And so this is waning. This is the best way to remember. So waning is going away. Waning. And waxing then. Okay? That's how I always remember it. It always gets mixed up, waning, waxing, stuff like that. But I always remember waning is going away. So that's how you do it. Okay, so now let's basically look at the phases of the moon. These are the phases of the moon now. All right? Okay. Now, suppose I want to understand a few things, right? Suppose I'm told that I am in the third quarter moon, for instance, right? So there's a few things I can understand here, okay? So the other thing I can try to understand, so this is dark side of the earth, right? Is suppose I draw this person here, a person here, a person here, and another person here, okay? All right, and this is basically, this is moving this way, and the moon's orbiting this way. So this is a sunrise, sunset. This is noon, when the sun's high in the sky, and this is midnight. Okay. Now, the other way to also keep in mind is that there are times associated with this as well, right? So this is 12 p.m. This is 12 a.m., right? It's midnight after all. Sunset, 6 p.m., right? Sunrise, 6 a.m. Okay, so that's easy. Okay, so now here's how we can basically do a lot, right? So, for instance, I can ask myself now, okay, the following question. When is the full moon highest in the sky? Okay, so full moon high in the sky. And then what time it rises, okay? And then sets. So this is easy, okay? I always like to think about it in terms of when it's highest in the sky first, because that's the easiest thing to look in this plot. So basically, I ask myself, okay, if I'm looking up here, right, will I see the full moon high in the sky? And the answer is no, all right. If I look here, then the full moon is in fact high in the sky. So when's the highest sky? It's the highest sky is at midnight. Okay. Now the other two are harder, right? When's it rise? When's it set? Okay. So now remember, you see stuff rise when you look toward the horizon. So if I'm at midnight, I'm going to look here and here. Basically, I'm going to ask myself, is anything rising or setting here, right? So for instance, okay. All right. So obviously, like usually that's not how the question is posed. The question is usually posed that, okay, if I have a full moon here, when does it rise and set? So I can ask myself, which one of these characters, if they look basically left and right, okay, we'll see the moon rise. Okay, and in fact, there are two answers here. Okay, when I see the moon, I'm going to see the moon at the horizon at this time, basically at sunset and at sunrise. Now, what's the difference? The difference is that basically because I'm rotating in this manner, at sunrise, actually the moon is setting. At sunset, the moon is rising. So this basically happens at 6 p.m. Rises at 6 p.m. and it sets basically at 6 a.m. Okay, so that's a relatively easy one. Full moon is always the easiest one. Okay, so let's do another one. Okay, let's ask another question. Right. Let me ask a question. So, for instance, let's look at the first quarter. All right. Okay, so highest, question mark, rise, question mark, set, question mark. Okay, so when's the first quarter moon rising, highest, rising, and setting? Okay, so this is easy too. Okay, so let's do, I always do highest first because highest is always the easiest. I ask myself, which one of these characters, as they look up in the sky, will know it's the first quarter moon rising? And the answer is basically it's this dude right here. Okay, so sunset, 6 p.m. Okay, Now, when does it rise? So again, I have to look left and right, left and right. I guess which one of these dudes, I look left and right, will basically see the well, not dudes, maybe they're called dudettes now. Okay, I want to be fair. We'll see the first quarter moon, right? And there are two answers again, basically be noon and midnight. Okay, but the difference is that I'm rotating this way. And so basically this one's rotating toward it. It's going to get higher and higher sky. This thing rotate away from it. It's going to get lower and lower sky. So this is rise, set. So rise at 12 noon, sets basically at 12 a.m. Right? Here's another thing to notice, right? The rising time will always come before the highest in the sky time, and the setting time must always come afterwards, right? So as long as you get that straight, that's always going to be the case. So basically, when does it rise? Well, basically for the full moon, well, it rises at 6 p.m. because that's before midnight. When it's set, basically it sets at 6 a.m. That's after midnight. All right. Okay, number 3. Now, okay, let's do a slightly more complicated one. Let's look at the waning crescent. Okay, so again, highest. All right, and then we will look at rise and set. Okay, so let's look at waning crescent. Okay, so now this is slightly more complicated. This is why it turns out asking the following question, when's the highest in the sky first, always make your life a lot easier. All right, so which one of these people, if they look up at the moon, will see it at highest sky? And this is none of these dudes will do it. There's only one person who can do it. It's this person right here. Okay, look up, you'll see it. Where in time is this person? This time is between sunrise and noon. So what's that? It's 9 a.m., right? So when is waning crescent highest in the sky? Well, it's between sunrise and noon, and so that's 9 a.m. Okay. When does it rise now? Okay, so now this is another hard one, right? So which one of these persons looking left and right will find it? Well, turns out none of these do. So you have to basically draw another person here, another person here. Okay. And this person looking left and right will see it. This person looking left and right will see it as well. Okay. When is this time? This time is between 12 a.m. and 6 a.m. So that's 3 a.m. And this time is basically between noon and 6 p.m. is 3 p.m. Okay. So when does it rise? Well, this one's going to rotate toward it, 3 a.m. When does it set? Basically 3 p.m. Right? Okay. Now, this brings up a very interesting and important point, right? So, generally, uh, um, the point in the sky when the moon spends most of the fraction of the time, right? So basically, these moons here spend most of the fraction of time in the second half of the evening. These moons here spend most of the time in the first half of the evening, right? In the first half of the evening. So basically, the moon is going to get full if the moon is basically up most of the first half of the evening. The moon is going to be starting to go away if the moon is up basically mostly during the second half of the evening, right? So that's one other point to keep in mind, right? So this is like the clearest, usually clearest illustration of doing this. You have to do a few exercises in order to understand what's going on. Okay, let's go back to our little slideshow now. All right, start from current slide. Okay, right, so this is just an example, not as good as the one I just did. All right, so here's this summary. The fraction of moon's disk that is visible is equal to the fraction of the night the moon is up. That's interesting. When the moon is on the first part of the cycle, waxing is up for the first part of the night. When it's in the last part of the cycle, waning is up in the last part of the night or second part of the night. Okay, so let's talk about one last thing, which is eclipses of the moon and the sun. Right. So when the Earth's shadow falls on the moon, you see eclipse of the moon. Right. So in order for this to happen, the moon and the sun have the opposite sides of the Earth. Right. And so basically, as a result of this, the moon can only occur when the moon is full. Right. All right. So here's an example of eclipses. All right. So that's eclipse of the moon. All right, so the moon has to be in the Earth shadow, which means it has the opposite between the Earth has between Earth has between the moon and the sun, and so this can only happen basically at full moon. And you have eclipse of the sun. Basically, the moon has between the sun and the earth, and so that can only happen basically when the moon is at new moon. All right. Okay, so this is close eclipse of the moon. Shadow of the earth covers the moon. All right. There are two parts of shadow, the umbra and the penumbra. All right. And so there's also partial eclipses of the moon because sometimes the moon just misses the umbra of the earth. It just misses through the umbra of the earth, and you get partial eclipses. All right. So here's an example of partial eclipse. All right. There's quite a bit of interesting stuff happening going on. So you see this red part. That's basically atmospheric scattering and basically diffraction of light, basically as it skims the surface of the earth. Okay. Now, what is interesting about this is that if you look at the Earth and the moon, you could actually sort of see the shadow of the Earth on the moon, right? So that's the shadow of the Earth on the moon. And what do you notice? It has a certain curvature of it, which is different than the curvature of the moon, right? So here's a sequence of image over 5-hour period. It takes about basically the moon moves about half degree every hour, so it takes about 3 hours to curve the Earth's shadow, right? And you can see basically the Earth's shadow is roughly about 3 times the diameter of the moon, right? And so basically, there was a Greek philosopher back in called Aristarchus, who basically used the size of the Earth's shadow. They in fact knew that the Earth was a ball by that point, to estimate that the moon's diameter was only about a third of the Earth. Right? That's about roughly correct. Okay. Now, on the other hand, basically every now and then there's an eclipse of the sun, right? And so in order for that to happen, the moon has to be between the Earth and the sun, right? And there are two parts of it, right? So there's part of it where the Earth will be in the umbra. So basically, those would be total eclipse. The shadow will be the moon blocks out all the sun, and there'll be partial eclipses. The moon blocks out only part of the sun in that case. All right. Okay, so here's a total eclipse of the sun. Beautiful. All right. Some space. Basically, you see where the umbra sits on the Earth. Right. It's a small part of the Earth. The Earth's much bigger than the umbra. Okay. And so basically, if you look, eclipses do not happen basically all that often because it only happens on very narrow portions of the Earth. And in addition, basically, 70% of the Earth's surface is water, so a lot of times you don't end up seeing it. Okay, and so here's basically an annular eclipse of the moon, right? So when the moon is farther than usual from the Earth, its angular size is slightly smaller than the sun, so it allows for an annular eclipse of the sun. Right. This could never happen for the moon because basically you got partial eclipses or total eclipses of the moon, right? But you can't have basically annular because the Earth's shadow is much larger than the moon. Okay. So how often the moon eclipses occur? So as we discussed already, the moon has to be for solar eclipse, the moon has to be between the Earth and the sun, so it can only happen at new moon. For lunar eclipse, that happens basically the moon has to be behind the Earth and the sun, and so it can only happen at full moon. All right. Now, what is interesting is that the moon's orbit is tilted about 5 degrees out of the plane of the ecliptic. Okay, so the moon is usually slightly above or slightly below the Earth's shadow at full moon, and the Earth is usually slightly above or slightly below the moon shadow at new moon. So basically, we just miss each other most of the time, right? If basically they were exactly on the ecliptic, all right, then we get a shadow basically all the time. We get eclipse basically we get a solar eclipse once a month and a lunar eclipse once a month. But that's not true, right? There's only 2 points which that's possible, right? Where the orbital moon lines up the sun, okay? And 2 points are basically where eclipses are called the nodes, right? So these are the nodes of it, okay? And so most of the time, basically, so only once every 6 months, basically, the line up from the sun to the moon lies in the line in the plane's moon's orbit. All right, and so basically, eclipses can only occur during these eclipse seasons, right? So it's only a few times a year, twice a year, basically, where it's favorable for something like this to happen. And so the moon has to be just in the right phase during those times of year for either a solar eclipse or a lunar eclipse.
Eclipses don't occur at every new and full moon because the moon's orbit is tilted slightly with respect to the Earth's orbit around the sun. As a result, at the time of month when the moon lies toward the sun, it may be below or above the Earth's orbit, and its shadow cannot fall on the Earth, nor can the Earth's shadow fall on the moon. However, because the moon's orbit keeps approximately the same tilt, a time will come twice each year when the Earth, moon, and sun line up so that eclipses will occur.
Okay, so also one other thing is that solar eclipses occur slightly more often than lunar eclipses, but they're only visible if you happen to be standing in the eclipse path. So as a result, basically, um, uh, um, you definitely don't see them as often, right? On the other hand, eclipses of the moon can be seen from anywhere in the part of the Earth that's in that part of the night. Okay. So basically, you see many more lunar eclipses typically than solar eclipses. All right, and